Okay, so let us continue our discussion with the notion of the cycle space of a graph this time. But before we go to that, of course, let us recall the things that we have seen, we have already seen. So in this section, we started off with a graph with vertex set V and edge set E, which of course is a finite graph, everything is finite. What we then did, we considered the set nu of G, whose elements are functions like this, functions from V into F2, where F2 is the field with two elements, a zero element and a unit element or a unity. These two elements of course are there in any field, but this is the smallest field because it has only them as elements. Then on this set we defined an addition and a multiplication by scalar like this. Say you take two elements f and g in this set and you take a scalar lambda from f2, which is obviously going to be either 0 or 1. What we then do, we define the addition like this. The sum of f and g is the function, just like f and g themselves, it's also a function from v into f2. What specific function? This one whose rule is defined like this. Evaluating f plus g at an input v, which will come from capital V naturally, means taking the sum of these two scalars f of v and g of v. Just like that, lambda f is that function from v into f2 whose rule is defined like this. Evaluating lambda f at v means taking the product of the scalars lambda and f of v. And it turns out that under these two operations, with this as addition and this as scalar multiplication, nu of G becomes a vector space over the field F2, and this is the vertex space of the graph. And then we considered another way of looking at the vertex space by recognizing that there is a natural one-to-one correspondence between nu of G as a set and the power set of V, which of course is the set of all subsets of V. And the specific correspondence is this. Say you take an element f from here, you make this correspond with this f inverse of 1, the inverse image of 1 under f. Does it make sense? Yes, because your 1 is coming from here, and because your f maps v into f2, so you can ask what the inverse image of 1 is under f, and by definition it is the set of those elements in V which get mapped onto 1 by f, and this is of course a subset of V, that means an element in the power set of V. Okay, now under this correspondence, not only are the elements of nu of G, that is this type of functions, get corresponded to these subsets of V, but the entire vector space structure that nu of G has gets transferred to the power set of V. That means we have addition here, that becomes something here. We have scalar multiplication here, that also becomes something here. And it turns out that the sum that we have here, vector addition, gets transformed into symmetric difference on this side. The scalar multiplication also gets transformed into something, but that is not something that we already know. In case of addition, it very nicely gets transformed into symmetric difference, and this itself then becomes a vector space over the same field F2, where now addition is symmetric difference, and these two vector spaces are isomorphic. So really we are not looking at a different vector space, but another version of the same vector space, and this is the version that we then keep using. In this version, if we consider vectors A and B, which truly are just subsets of V, then their sum is the symmetric difference of these two. That is A minus B, A difference B union B difference A, which if one wants can also be looked at like this. You can take the difference of the union and the intersection of these two vectors. One more thing, the zero vector in this case is the empty set as a subset of V, and the negative of the vector A is nothing but A itself. We have also seen that the dimension of the vertex space is nothing but the order of the graph, that is the number of vertices in V. And all these things that we have done for V, if we replace V with E, then also some such things will be true, and then we get the H space of G. If in place of V you have E, everything else is similar. And in this representation for the H space, the elements in the H space of G, we are not going to consider them as functions from E into F2, but rather as subsets of the H set E. That means our H space as a set is the power set of E. And now we define the cycle space of G in terms of the H space, like this. The cycle space, well, we should write the notation for the cycle space. The cycle space C, or C of G, in order to indicate it, the fact that it's the cycle space of G is the subspace of the H space of G spanned by the cycles or more precisely by the H sets of the cycles in G. Okay, so let us now see what this thing means. The cycle space of G is the subspace of the H space of G spanned by the cycles in G, or more precisely by the H sets of the cycles in G. Let us take one example. Say we have this graph whose vertices we label 1, 2, 3 and 4. So this is our G. Then the vertex set consists of these 4 vertices and the edge set consists of these 4 edges. 1, 2, 2, 3, 1, 3 and 3, 4. You understand that these are not 12, 23, not like that. These are shorthand notations for these more elaborate notation for the edge 1, 2, for example, which is just by definition which is this, but in short we write like this. Okay. So what is the edge space of G? By the definition of the edge space, it is the power set of E. As a set, it's the power set of E. That means the vectors in it are subsets of E. Now, when we are saying that the cycle space is the subspace of the edge space spanned by the cycles, in this graph for simplicity we have kept only one cycle. So when we say that the cycle space is the subspace spanned by this cycle, in this case for example, we do not mean the subgraph which is the cycle itself, but more precisely the edge set of this cycle. And why is that so? That is because, you see, by the way, what is the edge set of our cycle? F, say we call it F. It is the set of the edges that we have in the cycle. 1, 2, 2, 3 and 1, 3. This clearly is an element in the cycle space. In the edge space. And as an element, as a single vector, it will span a subspace of the edge space. And that is the cycle space of G. That's why we say more precisely by the edge sets of the cycles. Maybe there will be other cycles in other graphs, and each one of them, they themselves are not vectors in the edge space, but rather their edge sets are vectors, and they will span a subspace of this vector space, the edge space of G. That is the cycle space of G. And something else has also been mentioned in this connection by the author. Which is this. For simplicity, as a footnote actually, for simplicity we shall not always distinguish between the edge sets in the edge space of G and the subgraphs of G they induce. The language can become quickly very confusing, okay? You see, for simplicity we shall not distinguish between the edge sets F in epsilon of G. Whenever we normally see sets, we do not think of them as vectors, but in this case they are. When we say edge sets F in epsilon of g, that means this is a single vector in the H space. And the subgraphs v comma, I don't really know why the author is using this notation, but anyway, by this he means the subgraph induced by f of g they induce. So what he is saying is that we will most often not really distinguish between this f, which is a set of edges, and the cycle itself, which is the subgraph of g that this f induces in the graph g. But sometimes we will make the distinction. When we wish to be more precise, such as in chapter 8.5, we shall use the word circuit to denote the H set, circuit for the H set of a cycle. That means if we really want to be very precise, we would say that the cycle is 1, 2, 3 and its circuit is this f. That's how we are going to make the distinction whenever we do want to make a distinction. Okay, fine. So we understand what the cycle space is. It is the subspace of the H space of G spanned by all the cycles, where we really understand what by all the cycles means, rather their H sets. And now the dimension of the cycle space of G is sometimes called the cyclomatic number of G, about which I am sure there will be some result, but right now we can say one thing immediately. You see, just like the dimension of the vertex space of G is n, the number of vertices in the graph, the dimension of the H space of G is m, the number of edges in the graph. And because the cycle space is after all a subspace of epsilon of G, so this cyclomatic number will be less than or equal to the dimension of the H space, that is the size of the graph, or its the number of edges. This we can immediately say. And if the cyclomatic number becomes equal to m itself, then the cycle space becomes equal to they coincide, equal to the H space. Now there is this this proposition. it tells us, okay, so by definition the cycles induce the cycle space, but there is a smaller subset of the set of all cycles that also induces, I mean, or in other words spanned. These two languages get mixed up, the graph theory language and the vector space theory language. The cycles already span the cycle space, that is the definition of the cycle space. But among all the cycles, there are some even simpler types of cycle. They also span the entire cycle space, and they are called induced cycles. The induced cycles in G span the entire cycle space C of G. What are induced cycles? Say you have induced cycles are induced subgraphs which are cycles. That means, let me take one example, then it will be clear. Say we have a graph like this. Okay, 1, 2, 3, 4. There are cycles, we can see that, and you can consider the cycle 1, 2, 3, 4, 1, actually that cycle. It is not an induced cycle because it has a chord. If you consider the vertices of the cycle, then the subgraph those vertices induce is in fact, in this case of course, the whole graph. To make the matter non-trivial, you can take another vertex, say 5. Then the vertices 1, 2 and 3 and 4 of the cycle, they induce a subgraph of this whole graph, but that is not the cycle itself. This chord also gets included. So it is not an induced cycle. However, if you have a graph like this, a very complicated graph, something like this, there are edges, we don't really know how they are going, but in this graph, this cycle, in spite of having so many edges and everything, so many vertices, the cycle 1, 2, 3, 4, 5 is an induced cycle, because the vertices, if you consider those vertices, then the subgraph they generate, or the subgraph they induce in the graph is just simply a cycle. That is an induced cycle. So that means an induced cycle is a cycle that has no chord. I should perhaps carefully see if I have unknowingly introduced some chord or not. No, I don't think so. Okay, so this is an induced cycle, but this is not. So that means chordless cycles are induced cycles. So the claim is that the cycle space not only of course is generated by all the cycles, but in fact they are generated by this somewhat smaller set of induced cycles. And in the proof, just these words are given. So let me first write down the proof as it appears in the text, and then we will try to understand what the author means. By the definition, C of G it suffices to show that the induced cycles span any cycle with a chord. With a chord E. Induced cycles in G of course in G, because G is the only graph here, generate or so can I really write span? Yes, I can write this because in the sense of vector space span generate any cycle C in G with a chord, and this follows at once by induction on the size of the cycle, for which you can either you can take the size of the cycle either as its number of vertices or its number of edges, same thing, like this. But exactly how? Like this. The two cycles in the graph C plus E, when you consider the cycle with the chord, that have E but no other edge in common, but no other edge in common, are both shorter than C, and C is precisely their symmetric difference. And that's it. And now let us try to understand what the hell went on here. Some such things are there in the book. The book is littered with this type of proofs which look very sleek, very sharp, but there are things which need to be made clear. Okay, so let us once again go through the whole thing. We have the cycle space which is spanned by all the cycles in the graph, and we are saying that in fact the cycle space is also spanned by all the chordless cycles. So it's enough to show that in fact a cycle with chord, if we can show that a cycle with chord itself is spanned by chordless cycles, then that's just it. Then the chordless cycles themselves will span the entire cycle space. So we take a cycle C with chord E, and we want to show that this cycle C, only the cycle, okay, not the not along with the chord, only this cycle, but it's a cycle in which there is a chord. This type of cycle also is spanned by chordless cycles. That means what? That means that for this cycle you will find some finitely many, of course finitely many, because everything we are considering these spaces, everything is finite. So we will find finitely many chordless cycles such that this C will be equal to a linear combination of those chordless cycles in the edge space. That's what we have to show. And in order to show this, there is a sort of induction process that the author has mentioned here that we can apply on the size of C. How would that induction start? What will be the basis of the induction? Let us first try to see that. Because we are going to apply induction on the size of C, so we have to choose a shortest or a smallest cycle that we have in our graph. What happens if there is no cycle in the graph? If the graph is a tree, then what happens to the cycle space? Then the set of cycles in the graph is the empty set, and the empty set generates the trivial vector space consisting of only one element. In that case, the cycle space is also the trivial subspace of the edge space, and that thing is, we understand that. In that case, everything is vacuously true. So we consider a graph which has at least one cycle, so there will be at least one cycle having smallest size. Now you have such a cycle, say. We don't really know what its size will be, but there is one such cycle with smallest size. Can this cycle itself be a cycle with chord? No. Why? Because if you have a chord which joins some vertex of the cycle to some other vertex of the cycle itself, then you can find a smaller cycle, and in fact another smaller cycle. So then how can it be the cycle with the smallest possible size? That's why if in a graph you find a cycle with the smallest possible size, it will be a chordless cycle. That means it will be an induced cycle with no such chord. So that means if our size of C is the smallest possible, then the C itself is an induced cycle. Okay. Here, however, we are mentioning that we are considering C as not such a cycle, but a cycle with chord. But to in fact actually start the induction, let us not consider this for a moment. We are just simply considering any cycle, and on the lengths or on the sizes of the cycles itself we are applying induction. Okay. So in this case, because this itself is an induced cycle, it is spanned by all the induced cycles. How? You just the cycle itself is a scalar multiple of itself, where you take the coefficient 1, your field element 1 from F2. So that means we have the basis for our induction. Okay. Now say the claim is true for all cycles whose sizes are less than or equal to n. N is some integer greater than or equal to the size of the smallest cycle in the graph. This is our induction hypothesis. Now say you now consider a cycle C prime whose size is n plus 1. Okay. Now if it happens that C prime itself is an induced, it may happen. C prime itself, in spite of being such a big cycle, C prime itself is an induced cycle, then we are done. We don't have to do anything because it itself is an induced cycle. So just like the base case, we would then stop. Otherwise, there is a chord in C prime. say your C prime looks like this. Something like this. It may look like a hexagon, but you understand due to the presence of this dot dot dot, it's not necessarily a hexagon, which has a chord. So this is your C prime and this is E. Now, what the author is saying here is that the two cycles in C plus E is this subgraph. We may actually be in the original graph, which is maybe much larger than this, but we are concentrating on this cycle with chord. Now we can see there are two cycles here. This is one cycle, and on that side we have this other cycle. And excuse me, keep in mind that these smaller cycles themselves may also have chord. We don't care, okay? We are not taking into account, we are not distinguishing between cycles having chord or whether they are induced cycle. We are running the induction only on the size of the cycle, and we are not discriminating between the two types of the cycles. Now the point here is that this cycle has length smaller than n plus 1 because some partitions it has lost. That other cycle also has length smaller than n plus 1. So each one of them is a linear combination of induced cycles by our induction hypothesis. Now what happens to the original C prime? The original C prime, if you call this smaller cycle on this side C1 and this smaller cycle on that side C2, then C prime is actually the sum of C1 and C2. Why though? In our edge space, C prime is the sum of C1 and C2. Keep in mind that although we are saying cycles, truly speaking, we really mean the sets of the edges of these cycles, because after all we are in the edge space. But to not be endlessly precise about everything, we are just somewhat loosely saying cycles. So here what we are saying, C prime, or rather the set of edges in C prime, is the sum of the set of edges in C1 and the set of edges in C2, and you know that this sum is the symmetric difference. You can see why. That is because you are looking at these two edge sets. One of them has these edges and the other has these edges. Among these two sets, there is precisely one common edge, that is E. So from the union of these two sets, you have to remove the intersection to find the sum, which precisely gives us the set of edges of C prime. And by our induction hypothesis, C1 is a linear combination of some induced cycles, some C star, something like that. And C2 is also a linear combination of some other induced cycles. So now C prime becomes a linear combination of some induced cycles. So this completes the induction, and that's why the author is saying that by induction it follows that all the induced cycles also in fact generate the cycle space. It's like you have a topological space and you have a basis for the topological space, then you have a sub-basis also. So that sub-basis role is played by induced cycles here, or chordless cycles. Now Let's see the statement of the next result. We are not going to prove that result today, but let's see what the author has written next. The elements of C are easily recognized C means the cycle space. We are not explicitly mentioning the underlying graph. The elements of C are easily recognized by the degrees of the subgraphs, okay, by the degrees of the subgraphs they form. And in fact, we do not need arbitrary symmetric difference, but rather disjoint union. Moreover, to generate the cycle space from cycles, we just need disjoint union rather than arbitrary symmetric difference. And to justify these remarks, we have this next proposition, which makes precise the meaning of these remarks. 1 line 2. So here we have some 3 assertions which are equivalent to one another. The following assertions for are equivalent for the H set F in the H space of G. The first one is that F is a vector in the cycle space of G. The second one is that F is a disjoint union of cycles in G. Cycles in G. And number 3, the degrees of the vertices in this this is the subgraph of G induced by the edges in F, in the edge set F. The degrees of the vertices, all the vertices in this subgraph are even. Okay, so the first statement we of course understand that F is a set of edges which belongs to the cycle space of G. The second one says that F is a disjoint union of cycles in G, and you try to see what this actually means. F is a disjoint union. We already know that F is a linear combination of some cycles in G, but due to the fact that the scalars involved are just 0 and 1, that ultimately boils down to this statement that F is a symmetric difference of finitely many cycles in G. But a symmetric difference is not really a disjoint union unless the sets you are considering in the symmetric difference are disjoint themselves. However, it turns out that F actually is a disjoint union of some cycles in G if F belongs to the cycle space of G. And the third one is that any such F that is an element in the cycle space of G, the edges that are there in F, they will induce a subgraph of G. The vertices, all the vertices in such a subgraph will be even. These statements are equivalent to one another. If any one of them is true, then the others are also true. For example, in the actual proof, it has been proved like this: 1 implies 3, 3 implies 2, and then 2 implies 1. Okay, so that way the equivalence has been established. We will see this in the next graph theory update and further things which come after this. So with that, I am going to end the video today. You can either mail me, my address will be there in the description, or you can write in the comment section below what you feel about these things. And the next upload is today is Tuesday, so the next upload is on Friday, and we will go back to group theory from Herstein. So with that, I just sign off. So see you on Friday with group theory. Until then, this is me, Lucifer, from a mathematical group. Have a nice night.